Hello students, welcome to the lecture number 60 of our subject. Let us start a new chapter in this lecture, that is torsion. You must know about a variety of shafts fitted into the bearings. Let us show you some examples. You just imagine that this is a shaft, okay, and from both the ends it will be fit into the bearings. So now what happens when the shaft is trying to rotate in clockwise or anti-clockwise direction, but suddenly some restrictions are there, some jamming into the bearings are there, or maybe the choke up into the bearings, then due to that the twisting, like this twisting into the shaft is occurring. So that type of twisting movement is known as torsion, and due to this torsion the shear stress is induced on the material of the shaft. Okay, so that shear stress is known as tau. It depends on the material of the shaft. It depends on the modulus of rigidity of the shaft. As in the case of simple stress and strain, modulus of elasticity will be there. But when the shaft is rotating and the torsion or twisting movement comes into the picture, modulus of rigidity is an important factor to study. Let us start this chapter then. You can see the shaft or component of the bearing in the figure, in which the shaft can be fit into the bearing like this. Okay, so now basically what is torsion? In workshop and factories, a turning force is always applied to transmit energy by rotation. This turning force is applied either to the ream of a pulley keyed to the shaft or at any other suitable point at some distance from the axis of the shaft. The product of this turning force, remember the product means multiplication of this turning force and the distance between the point of application of the force and the axis of the shaft is known as torque. Which distance? Point of application of the torque and the axis of the shaft. Turning movement or twisting movement is known as this type of torque, and the shaft is said to be subjected to torsion. Due to this torque, every cross section of the shaft is subjected to some shear stress. So due to torsion, shear stress is coming into the picture. Let us see some theories based on torsion. The first one is assumptions for shear stress in a circular shaft subjected to torsion. We are assuming a circular solid shaft having diameter d. Okay. The material of the shaft is uniform throughout. Some material is not changing. If it is steel, then it is steel. If it is aluminum, then it is aluminum. The twist along the shaft is uniform. If the shaft is like this, then the twist at any point is uniform along the shaft. Normal cross sections of the shaft, which were plane and circular before the twist, remain the plane and circular even after the twist. Means the shaft is again made up of layers, one layer, two layer, third layer, fourth layer, fifth layer and bottom layer. But after the twist or before the twist, the first layer becomes first and the last layer will remain last layer. So the layer changes are not acceptable. Number 4 is that all diameters of the normal cross section, which were straight before the twist, remain straight with their magnitude unchanged after the twist. In short, these 4 are the imaginary ideal assumptions which is required for the theory of the derivation. A little consideration will show that the above assumptions are justified if the torque applied is small and the angle of twist also small. Let us see most important derivation, which is torsional stresses and strains. You can see in the figure that, now remember this is very complicated figure. Looking at the figure, this is the base, okay, rectangular base which is thrown over here, in which the shaft is fitted. This is the circular shaft subjected to torsion, torque T. You can see in the clockwise direction. Point O is the center of the shaft along the cross section. Suppose due to torsion, the shaft is, the point A on the periphery of the shaft is traveling the distance of A dash, A to A dash, and covering the angle theta at the center of the shaft. Extending A dash and A up to the back side of the shaft at point C, then it is forming an angle phi. You can see over here, this angle is phi, which is denoted over here. The length of the shaft is L, and looking at the side view, the cross section of the side view will be circular like this. This is the A to A dash distance traveled, and the angle subtended is theta. O is the center of the shaft. Twisting moment provided is T. Let us see some notations. What is T? T is equal to torque in Newton into mm, L equal to length of the shaft in mm, and R equal to radius of the circular shaft in mm. So these are the notations which are used for the numericals, which are used for the formulas. Let us see ahead. The same figure is carried forwarded on each and every page for your better understanding. The same figure is there, nothing new. What is AC A dash? You can see from the figure that angle AC A dash is having value phi in degrees. This is in degrees, okay, in degrees, 30 degree, 40 degree, 50 degree, like that. But angle AOA dash, which is theta, but this theta is in radians, okay. So this is by default notations in the theory. It is assumed like this and it remains like this. What is tau? Shear stress induced at the surface. What is C? C equal to modulus of rigidity, also known as torsional rigidity of the shaft material. So by taking this fundamental symbols, we are going ahead. Let us see again. We know that. Now what is shear strain? Actually, shear strain is not in your syllabus right now, because the chapter elastic constant is yet pending. But in simple stress and strain, you can remember that what is strain? It is a change in length upon original length, means change in dimension upon original dimension. So here, what is the change in dimensions? It is also known as deformation per unit length. So here, changes from A to A dash. Okay, change is from A to A dash. So A dash will be the deformation. And A dash means circular traveling. Circular traveling is along the length L. Okay, if the length is gradually decreasing or length is gradually increasing, then torsion will also depending on the length. You just imagine what happens if the length of the shaft is larger or greater, then the twisting is small or big. Okay, if the length of the shaft is shorter, then the amount of twisting is greater or lesser. This is all depending on the length of the shaft. So AA dash upon L, you can see what is AA dash upon L. From the figure, it is also known as tan theta, or you can simply denote is like phi, or tan phi equal to phi. Just remember all the things or forget all the things, but smaller value. You can see AA dash. What is AA dash? AA dash is the arc actually. Okay, so what is arc? Length of the arc. Length of the arc is equal to radius into angle subtended at the center. So from that also you can see AA dash upon L is equal to angle subtended at the center phi at the back side. Okay, while looking in the side view, AA dash is equal to R into theta. Here it is the radius R. R into theta will be arc length AA dash, R into theta. So this is the another notation. Now phi is equal to actually AA dash upon L looking from this equation. So phi is equal to AA dash upon L, which is equal to R theta upon L. It means AA dash is replaced by R into theta. Now why AA dash is replaced by R into theta? Because it is arc length which is equal to R into theta. So this both the formulas are corresponding to each other, means they are equal. They are subjected to only one formula, which is length of the arc, and it is radius into angle subtended at the center. From the back side, from the front side. Back side it is phi, and front side it is theta. Okay, let us go ahead. Now this is the new formula phi, which is shear strain. Actually this is the formula in elastic constant. The chapter is remaining yet to study for you. So as of now, you just remember this formula as equation number 2. Phi is equal to tau by C, where phi is equal to shear strain. Okay, phi is equal to shear strain, tau is equal to shear stress, and C equal to modulus of rigidity. So from this equation, tau by C is equal to R theta by L, because earlier we have seen that phi is equal to R into theta by L. So now just replace R over here and C will be cross multiply on the numerator. So what happens? tau by r equal to c theta by L. So this is the fundamental equation, tau by r equal to c theta by L. Just forgot this formula, which is not important for your point of view. So it is our first equation for the torsion. Tau by r equal to c theta by L. What is tau? Tau is shear stress. And what is r? R equal to radius of the shaft. What is c? It is modulus of rigidity, depends on the material of the shaft. Theta equal to angle of twist and L equal to length of the shaft. This formula is applicable for all the numericals. This is our first theory completed. Now let us go ahead for the second theory, which is strength of the solid shaft. What is strength of the solid shaft? You can see in the figure, this is the cross section of the solid shaft. Here R is the radius of the shaft, you can see over here. But we are interested to study something. So we have just cut one ring at a radius x from the center of the shaft. And the thickness of this strip, thickness of this ring is dx. If you have remembered moment of inertia, then in the moment of inertia for the circular section we have discussed the theory similar to like this. So dx will be the thickness of the ring. Let r equal to radius of the shaft in mm and tau equal to shear stress is Newton per mm square. Shear stress is developed in the outermost layer of the shaft. Okay. Now what is dA? dA means area of this minor strip which have been cut for our study. So what is the area of strip? You just imagine that you just cut this strip from this portion and unwound it. When the circular strip is cutting vertically and unwounded like this, then it will become a straight rectangular strip. Okay, so for the rectangular strip, when you unwound it, the unwounded length will be circumference of the circle, 2 pi x, which is the circumference of the circle. So 2 pi x into thickness of the rectangular strip means dx. When it wounded back, the dx will be the thickness of the ring. So 2 pi x into dx is the small area of this strip. Hope you can understand. You just cut the strip and unwound it. It will be rectangle. The rectangle length will be equal to circumference of the circle. The rectangle height is equal to thickness of that ring dx. Remember this thing. Okay. Now what is tau x? Tau x means the shear stress at this section, means at ring section, which is equal to tau into x by r. Why it is tau into x by r? Because at the outer radius, at the outermost layer, the shear stress is tau. Then what is the shear stress at the length of x? So by this tri-ratio, you can get tau x equal to tau into x by r, where x is the radius of the ring from the center of the shaft. Let us go ahead. Equation 1 and 2 will be utilized later on. Now, tau is equal to maximum shear stress. Now, main important thing is turning force. Turning force means you can imagine the force formula. What is stress? Stress equal to force upon area. So what is force? Stress into area. So here it is shear stress into area. Shear stress is tau x for this particular ring, and the area will be generated later on dx. Actually it is printing mistake. It is not dx but it is dA. Okay, it is dA like this. And what is tau x? As we have discussed, tau x equal to tau into x by r. Okay, in the previous formula, into dA as it is. Tau into x by r as it is now, and the dA means area of the ring is replaced over here, 2 pi x into dx. So by multiplication and rearranging 2 pi x upon r into x square dx is the final formula. Here it is not x, actually it is 2 pi into x square by r dx. Okay, x into x will be x square and dx will be as it is. Now what is torque? The torque for this smaller ring is denoted by dt. Now what is the formula for torque? It is equal to turning force into distance of element from axis of the shaft. Actually distance of element is also x from the axis of the shaft, means from the centroidal axis of the shaft, means from point O. So now the turning force is replaced directly 2 pi upon r into x square dx into tau. Here it is tau, actually this is tau, printing mistake. So final answer is 2 pi into tau upon r into x cube dx. It is the final equation number 3, which denotes dt for the ring portion only. But we are interested in finding the total torque of the shaft. So integrating from 0 to r, this ring is having radius x only. But we are finding the torque for the entire cross section of the shaft. So the limit will be 0 to outer radius r, and the remaining terms as it is, just constant out the constant terms 2 pi tau by r. So integration is for x cube dx only. Here it is x cube. Remember, here it is also x cube. Okay. So integration of x cube will be x raised to 4 by 4. Remaining terms as it is, 0 to r is the upper limit, lower limit. Just replace the limits, you will get your answer. In the final answer, you will replace r equal to d by 2, because r is the radius, which is equal to diameter by 2. And do the simplification, you will get the term like pi by 16 tau d cube in Newton into mm. So this is the torque. This is the torque, pi by 16 tau d cube. T is equal to torque, d is equal to diameter equal to 2 times radius, and tau is equal to shear stress for the shaft material. So this is the main equation derived for the solid shaft, which we will use in the numerical. What happens for the hollow shaft? See, this is the hollow shaft. The same theory is applicable to this also. This is the inside diameter d for the hollow shaft, you can see, and this is the outer diameter capital D. The remaining theory can be derived same as earlier, but this derivation is not in your syllabus. So just directly remember the formula like this. If r equal to outer radius, small r equal to inner radius, and tau equal to maximum shear stress for the shaft material, then T equal to pi by 16 tau. Pi by 16 tau is as it is. But in the solid shaft, it is d cube, capital D cube. In case of hollow shaft, it is capital D raised to 4 minus small d raised to 4 upon capital D. This equation is directly have to remember. Okay, but we can derive the same formula by the earlier method as the previous solid shaft. But it is not of importance. So just remember the formula directly. Let us go ahead. The power transmitted by shaft. Now this is the very simple formula which you have discussed in first year also. N equal to number of revolutions per minute. Okay, RPM. T equal to average torque kilonewton into meter. Work done per minute. What is work done? Work done is equal to force into distance traveled. All of you remember this. So force means T and distance traveled is 2 pi n. Actually 2 pi n t. Distance, force into distance is T, torque, and distance is circular. Therefore it is taken as 2 pi n in revolution per minute. Here it is written as per minute. So 2 pi nt will be the work done. Now what is work done per second? It is per minute. So per second the 60 will be divided for the remaining terms 2 pi nt by 60 kilonewton into meter. So it is the work done in kilonewton into meter. But we are wanting to find power transmitted. So work done in kilonewton meter per second is known as power transmitted. So itself this formula is power transmitted for the shaft material 2 pi nt by 60 is in kilowatt. Okay, here not is written that if the torque is in Newton meter, okay, if the torque is in Newton meter, then the work done will also be in Newton meter and the power done will be in watt. So remember the units also. This is the game of units and formulas. Actually one theory, either theory or one numerical will be asked in GTU exam from this chapter. This is very minor chapter which will be completed in 1 or 2 lectures only. Okay. This chapter consists of 5 to 7 marks in your GTU weightage. Let us go ahead. The last theory. Polar moment of inertia. What is polar moment of inertia? The moment of inertia of a plane area with respect to an axis perpendicular to the plane of the paper. Suppose this is the plane of the paper. My hand is the plane of paper and the axis perpendicular to it. Then moment of inertia about this axis is known as polar moment of inertia, which is denoted by capital J. Let us find capital J for the shaft only. We have discussed that tau by r equal to c theta by l. Tau equal to shear stress, capital R equal to radius of the shaft, c equal to modulus of rigidity, theta equal to angle of twist for the shaft, l equal to length of the shaft. And second formula is torque. Torque equal to pi by 16 tau d cube. Tau equal to shear stress, d equal to diameter of the shaft. Then making subject as the shear stress tau, then it will be 16t by pi d cube. 16t by pi capital D cube. Then comparing the equations, we will get 16t by pi d cube into r equal to c theta by l. Actually we have just replaced this tau in this formula. Okay. So answer will be 16t by pi d cube into r is equal to c theta by l. let us see what happens ahead. T by pi by 16 d cube r. So here the value is again replaced pi by 16 d cube. You can see from the previous formula, in place of numerator 16 will be transferred into denominator, so it will become pi by 16 d cube r c theta by l as it is. Okay, so now radius r equal to d by 2, so just replace r equal to d by 2, then the simplification will be like this: pi by 32 d into d cube becomes d raised to 4. So this term pi by 32 d raised to 4 is known as j. So j equal to pi by 32 d raised to 4 is known as polar moment of inertia for the circular shaft, for the solid only, for the solid shaft only. So final equation is T by j equal to c theta by l. But actually this c theta by l is over here, which is earlier tau by r. So we can say that the tri-ratio, the triplet formula will be like this: tau by r equal to T by j equal to c theta by l. So this is most important formula. This formula is also known as equation of torsion or torsion equation. Remember again, tau by r equal to T by j equal to c theta by l. What is tau? It is shear stress. What is T? Equal to torque. What is j? Equal to polar moment of inertia for the solid shaft, pi by 32 d raised to 4. What is the polar moment of inertia for the hollow shaft? So it is suspense. We will discuss it in the numericals only. C theta by L. C means modulus of rigidity, theta means angle of twist, and L equal to length of the shaft. So this is very short and sweet chapter. All the theories of this chapter is completed in one lecture only. So this is the 3 to 4 small theories for the torsion. In the next lecture, we will discuss some numericals. There are only 5 to 7 numericals based on these formulas only. So we will discuss it in the next lecture. Till then, students, have a practice of this lecture at your own. These lectures are already placed on YouTube, so it will be there for longer period of time. So you can revise these lectures at your own time. So till then, goodbye. Thank you very much.